Hi everybody, this is Cal with section 2.3, the completeness property of R. So what we've talked about in this chapter so far is the field and order properties of R. In section 2.3 and 2.4, we're going to talk about the other defining property of R, the completeness property. And in order to talk about this, we're going to talk about the idea of suprema and infima, so I mean, read the little introductory blurb on page 36, but it just kind of tells where we're at in the chapter. We introduced suprema and infima on the top of 37, and let me say you absolutely need to know what it means to have an upper bound for a set, a lower bound for a set, what it means for a set to be bounded or unbounded. There are a couple of examples right below definition 231. And you absolutely need to know, like by heart, like, really, really, it should be a part of you. Definition 232, the definition of a supremum, or least upper bound for a set, and of an infimum, or greatest lower bound of a set. And you should note that each of these definitions of supremum, of an infimum, has two parts, and those parts both need to be true for a number to be a supremum or infimum of a set. And the picture, figure 231, is in the middle of the page, is quite lovely. It really kind of captures what's going on. At the bottom of page 37, the book talks about how the supremum of a set is unique. There can be only one supremum. It even has a little argument for that. And it has notation for supremum and infimum, which I'll usually just call sup or inf. Not every set needs to have a supremum or an infimum, and the book spells that out at the top of 38. In the middle of the page, we talk about basically a few different ways to show that something is an upper bound. These are four different statements here in the middle of page 38 that let us show that that U is an upper bound of S. So make sure you understand where these statements are coming from, why they're equivalent. And what these statements let you do is state a couple alternate formulations for the definition of a supremum, which are covered in Lemma 233 and Lemma 234. And these are both important lemmas to understand what they're saying and why they're equivalent to the definition that was given in the first place. I urge you really to try to draw pictures of this like figure 231 on the previous page. On the very bottom of page 38, the book talks about the fact that a supremum of a set may or may not live in that set. It doesn't have to be an element of the set, but sometimes it is. And there are a couple of examples on the top of 39, which you should read and probably understand. On the rest of page 39, we actually introduce the completeness property, which is a defining characteristic of the real number line. And that is that every non-empty set of real numbers that has an upper bound also has a supremum. If there is an upper bound, there is a least upper bound. And you should think about what the corresponding statement for infima is. And that pretty much ties up 2.3. And since that was quick, I'm going to move right into 2.4 for the same video. Applications of the supremum property. So this section goes into a bit of how to work with suprema and infima, how some proofs involving them go. And I gotta say, suprema and infima are extremely fundamental ideas, and they're ones that are a little bit hard to get used to, so you're going to want to spend a bit of time absorbing the proofs in this section. The book starts out with examples in 2.4.1. And these are good examples to work through and understand how they work. Certainly this is the level of thing that I would expect you to be able to prove. Then the book goes into how suprema and infima work for functions, Essentially, when you talk about the sup or the inf of a function, you're talking about the sup or inf of the range of that function. And there's an example working with that idea in 242. It's a good example. I recommend that you try to write out the details that the book is omitting for part C here. Then we get into, starting at the bottom of page 41, the Archimedean property. These are absolutely fundamental. We're going to be using them throughout the term. And it's 4 restatements of the same property, property 243. You absolutely should know what property 243 is saying, and what its corollaries, 244, 5, and 6, are also saying. We're going to use these all the time. So do make sure that you understand what these are saying. At the bottom of page 42, the book goes into a proof of the existence of the square root of 2. Now, we showed in section 2.2, I believe, that if the square root of 2 exists, it's irrational. What your book is going to do here on page 43 is to show that the square root of 2 exists. And it does this through an argument involving suprema and infima. Basically, it defines a set and lets x be the sup of that set, and it proves that so we know that since this set has an upper bound, its supremum must exist, and the rest of the proof is concerned with showing that that supremum is the square root of 2. It does that by showing that, by looking at x squared, it shows that if x squared is less than 2, we can get a contradiction, and it shows that if x squared is greater than 2, we get a contradiction. When we put all that together, we get that x squared has to actually equal 2, which means that x, which is the thing that we showed existed in the first couple lines of the proof, must be the square root of 2. In general, you can modify this argument to show that any positive square root of a number a exists. And I recommend that you spend a little bit of time on this argument. This is one of these sort of painful mathematical arguments that you need to have seen and understood at least once in your life. I'm not going to say that you need to reproduce something like this without references on your own, but you do have to have some idea of what they're trying to do here and why it works. The book ties up section 2.4 with a discussion of the density of the rational numbers in the real number line. It says that basically, if you pick any 2 real numbers, there is always a rational number between them. That's what the density theorem says. It's also possible to prove corollary 249, which is that given any 2 real numbers, there is always an irrational number between them. So both the rationals and the irrationals are dense in the reals. These are pretty easy proofs. They're ones that I suggest that you make sure you understand. And that ties together 2.4. I'll join you in a moment in section 2.5.